Hi there, everyone. Welcome to today's IEAGHG webinar. My name's Samantha Needs. I'm a technology analyst at IEAGHG. So we'd like to welcome you all to today's webinar, which is an overview of the recent report on the value of emerging and enabling technologies in reducing costs, risks and timescales for CCS. I've just got a quick disclaimer slide here. So IEAGHG are a technology collaboration programme and we are part of the IEA's Energy Technology Network. We are completely autonomous from the IEA though, so any views expressed in this webinar do not necessarily reflect those of the IEA. And just a quick overview of the webinar today. I'm going to start with an introduction to the IEAGHG programme, and then I'll give a very brief background to this study. And then I'm going to welcome Catherine Orchard from Element Energy, who are the contractors for this study. He's going to go into more detail about the report and the work undertaken. And so back to the programme. The IEAGHG was established in 1991 and we are a member-based organisation with strong membership involvement. Our members meet twice a year and they set the strategic direction and the technical programme, and so they decide on all of the technical studies like the one we're going to be discussing today. And the programme has been around for 19 years now, and our main aim is to provide information on the role that technology can play in reducing greenhouse gas emissions from the use of fossil fuels and biomass, with CCS being our main area of focus. And we do pride ourselves on providing information that is objective and independent, that is policy relevant but not policy prescriptive, and work that is reviewed by external experts. And just some of our main activities are detailed on this slide. So we have published over 340 reports and technical reviews on all aspects of CCS. Our international research networks span a wide range of areas and facilitate international collaboration and knowledge sharing. Events such as the Post-Combustion Capture Conference Series and the GHGT Conference Series are popular and very well attended, with the latter having established itself as the principal international conference on greenhouse gas mitigation technologies, especially CCS. And our international CCS summer schools have been running now since 2007, and the 14th in the series was meant to happen this year, but obviously because of COVID-19 it's had to be postponed by a year. So the 14th summer school will be held next year in Indonesia. And this slide just illustrates how IEAGHG have and are continuing to contribute to global CCS efforts. So we work with the IEA, the CSLF, the IPCC, ZEP, the London Convention, and also ISO. And I did mention earlier about our GHGT conference series. So this is the flagship event of its kind. It has been postponed to from its normal October time of this year to March 2021, so take note of those new dates, the 15th and the 18th of March next year. And we are monitoring the global impact of the coronavirus situation, and we'll be making a decision on this event in the coming weeks. Either way, the event is still going to be taking place, whether it's in person in Abu Dhabi or virtually, but it will be happening either way. So you can keep up to date on all of this by visiting ghgt.info. And the IEAGHG programme is able to do what we do thanks to our valued members. And we currently have 37 members across the world, made up of countries, companies and organisations. Just a quick note on today's webinar procedures. As attendees, your mics are going to stay muted throughout. If you do have a question for our speaker, please type your question into the question tab as indicated on the right. You should all be able to see that in your control panel. And at the end, given the time you have, we'll try and get through as many questions as we can, but apologies in advance if we don't get to yours. And also please note that this webinar is being recorded and it will be made publicly available on our YouTube channel shortly after the event. And on to a bit of motivation and background for this study on the value of emerging and enabling technologies in reducing costs, risk and timescales for CCS. That number there, 2020-05, is just the IEAGHG report number. So now onto the background of the study, a very, very brief background. CCS, as we know, is a proven technology that is key for achieving global climate change targets. And not only does it directly mitigate emissions from industry, it also enables wider deployment of other low carbon technologies. However, the high capital costs and risks associated with large-scale CCS have led to some delays in supply chain development. So accelerating the rate of future development of is utmost importance, and it requires technological advances to support cost-effective deployment and operation. Current R&D into the reduction of cost, risks, timescales and challenges primarily focuses on more conventional and perhaps more established improvement processes or methods. Emerging and enabling technologies, however, do have the potential to offer more opportunities for cost and risk reduction. Diverse technologies and platforms developed outside the related sector are now helping the energy sector to reduce costs, risks and timescales for CCS projects, both during the planning and implementation and operation phases. CCS stakeholders may not necessarily have access to up-to-date information on these new enabling technologies, and this study intends to help further the information in this field. Now, the main aim of the report was to explore and identify which digital and enabling technologies may offer benefits for commercial scale CCS deployment. This work was a horizon scanning exercise, which included a literature review and case studies to begin with, and then it assessed the relevance and impact of the potential technologies, carried out quantitative modelling on the impacts on costs, and then looked at the qualitative impacts on potential risks and challenges of CCS projects. And a wide range of these technologies were considered and then broadly grouped into 6 categories, which you can see in these lower bullet points here. So we've got robotics, drones and autonomous systems, novel sensors, digital innovations, VR and AR, additive manufacturing, and also advanced materials. And as I mentioned earlier, this is report number 2020-05. So if you do want to request a copy of the report from IEAGHG, you just need to quote that number. We published a report in July this year. And as I did mention, Element Energy were the main contractors with support from Imperial College London. And now just to introduce you to our speaker today. Catherine Orchard is a senior consultant at Element Energy with experience across a wide range of sectors. Her expertise includes carbon neutral strategy development, business case analysis and policy development. Catherine has a PhD in materials chemistry from Imperial College London and has 10 years of technical scientific experience in areas including CO2 utilisation and sustainable fuel generation. So I'm going to pass things over to Catherine now for a more detailed overview of the report and work done. Thank you.
Okay, great. Thanks very much, Sam, for the introduction and for the opportunity to talk about this study today, which we very much enjoyed putting together and working on. So before I start, I just wanted to give a brief introduction to Element Energy ourselves. We're a specialist low carbon energy consultancy, so we work across all major low carbon energy sectors, so of course including CCS, ranging from energy networks to transport and the built environment, and obviously increasingly looking at synergies between each of these. We work on a range of different projects for a variety of clients, ranging from public sector to private sector. So we are, of course, not digital technology experts ourselves, but as Sam mentioned, we were supported by input from researchers at Imperial College with expertise across robotics, 3D printing and AI. But also throughout the project, we engaged extensively with different stakeholders and are very grateful for their input, both in guiding our research and their insights. So what I'd like to do talk to you about today, I'd like to start by giving you a broad overview of the emerging technologies that we looked at, so their key benefits and applications specifically for CCS. And then I'll talk about the quantitative modelling that we did, looking at the impacts on costs, and then briefly touch on the risks and challenges and the benefits that technologies can bring here. Okay, so as Sam mentioned, we looked at a broad range of technologies that we grouped together in these broad categories. Here's of which 5 we would consider digital technologies, largely because they use developments in software or digital platforms. And then the final one is advanced materials, so that's more physical systems and materials that will bring benefits. And although we have broadly categorized them here, in practice they're highly interrelated, and developments in one sector will bring benefits in others. So primarily developments in sensors will underpin a lot of innovation in robotics and autonomous systems, as well as digital innovations. And so we looked in this horizon scanning exercise for all applications in both the energy sector and beyond that would be relevant for direct inclusion in CCS projects. So we acknowledge that there would be other sectors that where these are being deployed that may also bring benefits indirectly to CCS projects, but we mostly focused on the direct inclusion. Okay, so to start with robotics, drones and autonomous systems, we group together as a range of physical systems that are used to carry out specific tasks. So they're typically fitted with a range of devices to bring functionality. So from cameras and sensors to collect data, to material deposition devices for remote repair. And so most people, I think, are familiar with drones, but it may range from that to robots that can go into pipelines or even underwater or autonomous vehicles. And so the key benefit really we see for these is in remote operation. And that particularly lends them to so monitoring, surveillance and maintenance. And that's reflected in the applications that we considered. And so by operating remotely, remove one of the human components, it represents a very low cost method of going to a site or surveying along a route. And so that can also reduce the time required for a particular inspection, maybe removes some of the additional procedures required. So for example, looking at height, you don't need scaffolding, you may not need fewer people, and it might allow you to access spaces that you couldn't otherwise do safely. We also see the key benefits in collecting better data by having a range of different sensors on board. You can collect more comprehensive data, which allows better analysis and long-term learning later. But also, quite key to that is that if they're lower cost than traditional monitoring procedures, that means you can do them much more continuously or frequently, which allows you to monitor, say, a component or a particular asset and reduce the risk of failure on the way. And so one of the applications is being developed in CCS specifically is for autonomous underwater vehicles, specifically looking at monitoring CO2 at storage sites offshore. And that can provide better confidence in projects and address risks in those areas. Okay, so the second group is in novel sensors. And as I mentioned, they're a key technology. I think we could say confidently they're everywhere already, but they're quite key, particularly for robotics and digital innovations. So we're trying to fit something to a robot or a drone that might then go off to do a particular task, as well as a standalone technology in their own right. Excuse me. And really developments in this area are targeting improved capabilities, so better sensitivity, accuracy and efficiency of measurement, as well as novel measurement techniques, or usability, so reducing cost, weight or power requirements. So for example, in taking one of the pictures that we have here is on the left there is of a subsurface sensing device, where normally they are wired together, and it's quite costly and time consuming to distribute them across an area. By making them wireless, they're much cheaper, can be just deployed at much better resolution, so far more of them can be put across an area and you get much better data collection. And so that, particularly for CCS, the applications we see are either directly in sensing something along the supply chain. So we've included gas sensing and specifically looking at CO2 detection to look for leaks across the supply chain. This has been investigated both for pipelines and in the marine environment, and corrosion sensing, so monitoring in situ different assets. Again, that reduces the risk of failure of themselves. It can improve confidence. And by doing it in situ, there's less disruption than might otherwise be experienced. But then the key application really for CCS is in subsurface sensing, and that's applications particularly in storage, site appraisal and monitoring. So looking at better understanding the CO2 plume and storage properties, either giving increased confidence before storage begins and during, as well as post-closure. And then under digital innovations, we've considered kind of all software applications that we see would enable better productivity, enhance connectivity and automation and optimization of processes. And under this, we look specifically at Internet of Things, so collecting continuous or near continuous data that can then be used for various purposes. Artificial intelligence and machine learning, which uses algorithms to interpret that data and either generate insights or responses if we're looking at something that would then be automated. And then also we included blockchain, which is a method of storing data and monitoring transfers. So that specifically in our case, we're looking at, or the application we saw as most beneficial is smart contracts. So for example, looking at the European trading system where you would need to confirm storage from a capture plant across the supply chain, that might be somewhere that distributed ledgers would be useful. And as we've set out in the main applications that we see are in optimization and automation, where you're reducing costs, again, removing that's one of the human components, and also you have improved efficiency and potential upskilling of staff if some of the more manual tasks are being taken on by an automated system. Predictive analysis is a particular strength of artificial intelligence. So where you might predict behavior to enable insights, for example, on how best, so in the oil and gas industry, it would be how best to use an oil and gas field. Potentially that could translate to CO2 storage to allow better management of storage sites as they continue to be used. And predictive maintenance, it's also a very powerful application of AI where you're learning to use sensing data to predict and prevent failure, allowing much more efficient maintenance schedules. We've also included simulation and virtual commissioning. This includes things such as building digital twins, so where it's a digital or virtual model of either something you're going to build or that exists already to enable monitoring of how it's performing. But that's also included in virtual commissioning, where you can build something ahead of time, carry out commissioning to make the whole process much more efficient. So again, we're looking at key benefits of reducing risks of failure, costs of operation, and optimizing the utilization of assets and decision making. So virtual reality or augmented reality technologies are both immersive technologies that either simulate an environment or augment it by displaying data, for example, on their visual field, allowing someone to talk to them and share the view that they have to enable joint processes to be carried out. And for the examples of these are, so the picture on the right there is someone with an AR helmet that's allowing an expert from onshore, for example, contacting someone on an offshore site to enable them to fix a part themselves rather than flying someone out to help on site. And that's really one of the key benefits that we see is in remote and enhanced operations. So you're reducing the cost of having to send people there, reducing the time, potentially downtime of a plant or operation while waiting for someone to go there. And you're improving safety. Again, if you can operate remotely, then a person doesn't need to be in a particular environment that may not otherwise be safe. We've also included enhanced design and improved training. That both, this is looking at simulating a process or a component which allows better design or a very low risk, low cost design. You can operate something without making it first, and you can train your staff more rigorously without the risks associated with that, and less time spent doing that. So yeah, as we've said here, they're reduced costs and improved standards from both of those applications. Okay, so additive manufacturing can both enhance performance and reduce manufacturing time. So additive manufacturing, also known as 3D printing, is the process of creating objects by layer deposition. So essentially using software to communicate with a 3D printing arm to build something from the bottom up. And one of the key features of additive manufacturing in particular that's to bear in mind is that the costs or upfront costs may be higher or lower than traditional manufacturing, but its real value lies in the gains in performance and reductions in lead times in doing processes. So what we mean by that is that, for example, key benefits are in creating complex geometries, so you're not limited by, or not as limited by what you can do with machining. You can build something with a complex or high surface area, for example, that you couldn't otherwise achieve. So it means that component design can be much more free, and you can be driven primarily by the functionality that you're trying to achieve rather than by how you make it. And that one of the applications in CCS that's being used in so far is in the printing of capture materials themselves, where you're targeting very high surface areas for improved CO2 absorption, but also printing of different capture components such as heat exchangers and contacting columns. Again, looking at improving contact areas, which can in turn reduce degradation of solvents if it's a solvent-based system, and that will reduce costs of waste management and emissions. You can have fewer parts. Again, if you can print much more of your material in one go, you have fewer parts. That improves your durability and lowers costs for maintaining it. Again, there's less waste because you're not machining, you're not losing any by removing it afterwards. And then there's also a very fast switch over manufacturing lines because it's software driven, rather than looking for, say, a physical mold or a machining process. It means you can very quickly make a switch to a different component, which can reduce lead times for producing components. And in the case of where you might use that to just print spare parts when you need them rather than buy a stock at the beginning of a project, that means you've got lower sunk capital. So yeah, the key applications we've considered here are rapid prototyping, which might be in design of components, but may also be used ahead of construction projects. That's an application that's been in the oil and gas sector to speed up commissioning, spare parts inventories, or replacing those with printing, and also component optimization, as we said. And then in the advanced materials category, as I said, we focused on two specific types of advanced material, and that's nanomaterials, which are materials with at least one dimension on the nanometer scale, and also composites, and that's materials that combine two or more different materials to generate something new that has either novel properties or improved properties. And these are two very broad categories of materials. There's a very wide range of applications of each of these, but to narrow our focus, we limited it to 2 very specific applications that we thought were particularly relevant to CCS. And that's in subsurface wetting for nanomaterials. So one of the key benefits of nanomaterials is that they have a lot of surface area, and so they can have novel properties compared to the bulk material, but also can then affect things such as subsurface wetting. And that's something that's been investigated for enhanced oil recovery, although is only at the research stage at the moment. And the other for composites, we look specifically at composite pipelines. So these are pipes that are primarily, they're built up by additive manufacturing. They're a combination of fibers and plastics, but enable they have much better tolerance of impurities than conventional pipelines or metal pipelines. They're much lighter to roll out, so reduce your transport costs, and can be corrosion resistant. And so it's worth mentioning that those in particular are unlikely to be used to replace large transmission pipelines, but they're particularly relevant for storage in the sense of replacing flow lines and in the injection process. Okay, so hopefully that's given you a flavour of the types of benefits that these technologies can bring. Obviously, it's worth acknowledging that they will also bring new risks and challenges that have to be mitigated. And we've set them out here, but just to pick a few rather than going through all of them. One of the key ones is obviously introducing digital components to a process or plant brings the risk of digital failure, which adds the risk of causing shutdown. And also related to that, there's system security. There's the added vulnerability to cyber attacks that needs to be mitigated. Data speed and connectivity. A lot of these technologies rely on transferring data, and particularly looking at where they have the most benefit is often in remote areas where you would not expect your Wi-Fi to be particularly great. So that there are research activities into ways that can be tackled as well. And also worth mentioning employment impacts. So we're talking about reduced costs in many cases because you're removing a human component, and that has the risk of job losses. But with the added flip side of that is that with upskilling of the requirements for the humans in the process, that may attract different or a wider range of people to that sector than would have been otherwise. And then in terms of additional barriers, the standardization and acceptance. So it's overcoming project developers' reluctance to put new technologies in, and establishing standards that mean that they can be, to build trust and know that they can be measured in a standardized way. Okay, so from the horizon scanning exercise, what we did was to then take all of those benefits and translate those into cost reductions. So just to give you a very brief overview of the way that we did this, we defined some base project costs for a range of different archetypes across capture, transport and storage. We broke these down further to identify really the relevant components that might be affected by digital and enabling technologies, to make sure that the key impacts that we were projecting were reflected more reliably. We then estimated the impact of each technology on each component and applied that as a percentage cost reduction where relevant. And as we mentioned, that there are some sort of additional benefits that aren't traditionally captured in literature costs of plants that we've added to better reflect the value of some of these technologies, and that includes downtime. So reducing downtime, either unplanned or planned, for maintenance or through unexpected failures, is something that is a benefit of several technologies, and which we represented as a cost of additional carbon emitted during that time. CO2 supply chain losses, so where we're measuring for potential leakage or otherwise losing it from the system. We've included that again as a cost of carbon, and then the verification of carbon stored. As I said, if you're a capture plant, for example, was adhering to the emission trading scheme, we've tried to include what the benefit of that would be. And since the applications are so varied or vary so much between the different components, we treated them each separately. So we kept capture, transport, and storage separate. And we just included a range of archetypes within each one to ensure we captured the benefits across different industries. And just a small note to say that future developments such as modular systems, we haven't analysed in detail, but we do touch on qualitatively in the report. Okay, so the main findings are primarily that the benefits are projected to be realised gradually. So the greatest cost savings are going to be from 2030 out to 2040. And this is a result really both of the time frame of technology development, the maturity of the technologies now, and the development timescales of CCS projects. So we've tried to account for the length of time in development, construction and operation. So for example, a plant that is going to be starting operation within the next 5 years or so will have already completed or would be about to complete the front end engineering design. And so there would be limited scope for including additional technologies in the project at that stage. But then also there are perhaps few that would affect the construction and capex at this point, or available to do that. So the main applications would be in affecting operational costs. Whereas for some technologies also that reflects the fact that the expected cost reduction impacts would increase with time. So for example, going from a manually operated drone to a fully autonomous system later would bring better cost benefits, or we would expect them also to improve with time. And so that's reflected in our time series. It's probably worth also pointing out for the capture plants that the base costs decrease with time as well. That's ongoing from a first of a kind to a nth of a kind project. So we've tried to capture the different impact that they'll have with general improvements in capture technology over time. Okay, and across the CCS chain, the largest absolute cost savings are in capture, whereas the largest relative savings are in storage. That's primarily because capture technology, or the capture site itself, has the highest costs of anything in the chain to begin with. So even modest reductions in cost there will give quite a large reduction in cost in general. But it's also worth considering that while the majority of CCS costs are CapEx, the majority of technology applications affect OpEx, so it's reductions in maintenance costs or other processes that happen once a plant is operational, or in the case of storage, it's monitoring after the site's closed, for example. And so actually what we tend to see is that the base costs really only see quite modest reductions overall. And then most of the cost reductions that we project come from these additional cost components that we added. So those associated with downtime and supply chain losses of CO2. So I think that really reflects some of the real value there of what these technologies are bringing in terms of impacting operations. So overall, digital innovations contribute the largest cost savings, both in capture and storage, whereas pipelines benefit most from robotics. And that's largely due to, so in capture and storage, a large amount of that comes from predictive maintenance. In storage, we included an aspect of AI-powered drilling, for example, or some other methods that may well impact the cost in the construction phase. and in appraisal. Whereas for pipelines, the main technology and bringing cost reductions is robotics, and that's largely from monitoring above pipelines or within pipelines, you could say, and generally reducing maintenance costs. And overall, across the CCS chain, we should say that digital innovations contribute to reductions in 8 of the 10 components, with the largest absolute cost reduction. So that really has quite a high impact. So we did include in one of our applications autonomous shipping, and in the CO2 shipping chain, that is the application that dominates the potential cost reductions. So looking at specifically at the ship itself, although the capex of the ship may increase, the operational costs may reduce by 20 to 30%, depending on discount rate applied. But overall, these OPEX savings are largely outweighed by that increase in capex. And when you consider the full chain, including liquefaction at shore and storage and other components that are required to take CO2 to the storage site, it actually makes an overall very small cost reduction. And so what we see there is that although benefits are going to be realized by CO2 ship operators, it's really very unlikely to impact the role that shipping is likely to play. So there will still be cases where CO2 shipping has a benefit over pipelines, but overall that isn't going to change. The balance between the two is not going to change much by applying these technologies. So to kind of take that further, we tried to assess what the global impact of these cost reductions would be, and what does that look like in the context of deploying CCS at scale. So we took the 2-degree scenario from IEA projections, which shows that in order to meet the 2-degree scenario, we need to be capturing close to 4 gigatons of CO2 per year by 2040. And that's distributed largely across the power sector, but also other industry. And when we applied the cost projections to this trajectory, excuse me, we find that you have potential cost savings on the order of hundreds of billions of dollars. So that's in terms of cumulative global savings, where 8% of that is in capex. Most of it is in quite a large amount is in OPEX, reflecting again the main applications of these technologies, and close to half is due to the carbon costs, which are associated again with benefits in downtime and supply chain losses. For capture plants, the largest savings are in power CCS, possibly predictably, as these are largely where a lot of the CO2 savings, CO2 storage needs to come from. And more than half of them are due to digital innovations. Again, this is largely due to our applications in predictive maintenance and analysis. Okay, so that was our quantitative analysis. So then we went to look at the risks and challenges faced by CCS, and what we find is that, or our feeling was that the main relevant risks that could be tackled by these technologies relate to technical viability. So there are a range of political and financial risks and challenges faced by deployment that may either directly or indirectly be impacted by some of these other risks that we'll just cover briefly now. But primarily we thought it was technical viability. So for example, in terms of integrating CCS into existing plants, where there may be issues in terms of, so for power plants, it might be challenges in closing down and starting up capture and power generation. So where we saw an application there was in AI-powered automation, where you can respond to external signals such as price changes or grid demand much more quickly and keep both systems more aligned. In terms of industrial plant integration, it's often more to do with physically putting the CCS plant in place. In there, we see applications for virtual commissioning and design that would enable more efficient design to reduce those issues, and again automating processes to allow more efficiency of them operating together and coordinating. Where nanomaterials can enhance wetting, the great promise of these, or the premise of using these, is to improve accessible pore volume, so that might allow greater utilization of each field, or each storage field each time, and allow greater storage capacity, allowing predictive analysis to maximize storage along the way. So this is kind of related to the way that it can be used in the oil and gas sector to more effectively extract oil, again, with then looking conversely at putting something into a well to maximize the storage and improve business case and reduce the need for further storage. And again, similarly, improving storage capacity in more modeling techniques would do that. We've included something about competition for staff that might be improved by automation or by doing things remotely. And then a key one was in potential for CO2 release, and the need to be more confident of, or to prove confidence in storage for long time storage, and then also avoiding any kind of isolated releases. So again, we're looking at different sensing to ensure that those are reduced, monitoring regularly, and also potentially modeling. And then we did look a little at lead time, at timescales, and our opinion was that there's limited evidence for reducing timescales of overall deployment of projects. So we see that there are some time savings that could be realized for individual projects, so streamlining prototyping or commissioning, or etc., that might reduce costs and times at the design stage, and again reducing lead times during construction or potentially during operation. But we feel like the impact is typically expected to be quite small, so months or less than a year primarily, whereas that we don't feel that really contributes greatly to the huge challenge of coordinating, for example, the long timescales in getting capture and storage coordinated. And these are still going to be part of a chain that has to be coordinated in that way, and it's likely that there will still be issues that will allow that to be the case. And we've kind of mentioned that developments in seismic analysis could potentially accelerate storage appraisal, but there's no precedent for this within other sectors, and largely that comes from the case that if we're looking for something like AI-powered analysis or appraisal, and it relies on huge amounts of data to be collected, which currently just isn't there. So it may be helped as time goes on and more sites are developed, but we don't see that we don't have evidence for there being a key impact there currently. However, of course, the disclaimer there is that there's, of course, a time there may well be disruptive developments that we've not foreseen here that could bring huge impacts. Okay, so just to very briefly summarize, there's a wide range of relevant applications across the chain, and they bring a lot of benefits from related sectors to CCS, and can bring significant reductions in costs. but these are largely expected to be realised only later from 2030 onwards. But on a global scale, up to 2040, that's cumulative savings of almost 200 billion in the lifetime costs of projects. Risks and challenges may be reduced through using these technologies, but in terms of timescales, we expect that to be relatively small. And with that, I thank you very much for your attention and welcome any questions. Hopefully I'm on time.
Thank you very much, Catherine. You've got plenty of time. Thank you. We have had a few questions actually, so I'll jump straight into those. So the first one we got was, if you could answer, how would any one of these technologies improve the performance of a solvent or sorbent?
Yes, that's a good question. So we didn't look specifically at improvements in solvents themselves. So we would that's an area that has been looked at. You know, that we would consider that's kind of a conventional way that capture technologies have been improved is looking at improvements in the solvent or itself. But so we could imagine that, for example, as I mentioned, there are some applications in additive manufacturing to look at improving heat exchange in solvent-based systems, and so there it's something that can perhaps reduce the amount of solvent that you need if you can improve the surface area, surface area to volume ratio, and therefore you need less of your material to deliver the same performance. But you might also, if you have much more efficient heat exchange between the solvent, then you reduce degradation. Maybe that's less solvent you need to replace with over time, and it's less waste stream that you have to deal with. Hopefully that answers the question.
Yeah, I'm sure that's great. Thank you. Okay, so next question. Autonomous shipping. Now, it sounds quite dangerous, perhaps. Do we think that regulators will actually allow such ships to sail into and out of ports autonomously?
Yeah, good question. Yeah, so we didn't look specifically at the regulations around this. However, so Rolls-Royce and Yara have both progressed with demonstration vessels. I would say that in terms of regulation, if you were comparing it, say, to road transport, I would say the regulatory barriers are much less for shipping. And it's allowed these technologies to progress a bit further. So I think we're closer to having autonomous ships on the seas than we are autonomous cars in the city. But yeah, it's certainly something that we didn't look specifically at, but would be a very interesting aspect to look at in much more detail.
Great. What have been the best ways to support the adoption of these technologies in other sectors?
Yeah, that's a good question. So I guess that is very relevant for how would we make sure that they came through in CCS. I would say that, I mean, one aspect is that those that have been deployed widely, so for example using drones to do inspections and maintenance, I think the cost benefits there make them quite easy to choose. I don't think there were regulatory barriers to doing that, and really the main problems that came up were in cases where maybe you need standardization and to ensure that they can be carried out for specific tasks. So for example, I'm thinking specifically of, say, shipping tanker inspections, which have to be done regularly and to a specification, and that specification kind of dictates that you would need inspection by a person and in specific criteria, whereas but then in order to do that using a drone, which may be quicker and cheaper and safer, there needs to be development in those regulations, and I think there have been strides to do that. And so that comes down to kind of industry acceptance and putting standards in place. And that also applies to things such as additive manufacturing and with the, for example, the composite pipelines. Some of that comes down to trialing them, making sure that industry has confidence, as well as developing standards to make sure that, again, people are confident in using them. So I think from a political perspective, it's not something that has required intervention, but it's more comes down to proving them as technologies.
Mm-hmm. Yeah. Okay. Can you please elaborate on what is meant by virtual commissioning and explain how this is expected to reduce risk? Is there not more risk when human contact is removed from the process?
So that's something where, again, you build a virtual environment that that replicates the system that you're looking to commission. So it means that it's not something that takes away the human component entirely. What it means is that you can go through the commissioning procedure virtually first before you go and then do it in real life. But that means that you avoid and many of the pitfalls before you get to that point. So it would reduce costs in terms of, say, if it's a procedure that requires consumables, you don't lose any of those through iterations, taking out some of the problems. It also means maybe your staff are more used to carrying out the procedure, and so it's quicker and more efficient at the point where you do it in reality.
Yeah.
So yeah, we're not saying don't commission in the normal way, but it's just done virtually first.
Yeah. Okay, great. And I've just had a point come in. It's not so much a question, but a point that during COVID, remote surveys on vessels carried out by vessel crew is actually currently up by 30% at present. That's quite an interesting little fact. So thank you to the person that popped that in the messaging part. One last question. I think we've got time for one more. Those of us who are advocating for CCS often talk about the value of CCS to the economy in terms of jobs for design, engineering and construction, and jobs to operate the plants. How do we reconcile these cost savings with the value to the economy business case?
Yeah, great question. And one, I suppose that would require probably a study by itself to really look at where jobs are created. I suppose we have to be careful in where how we're looking at changes in employment. I suppose that the comment I made about upskilling means maybe it just means that if some of the types of jobs have changed, maybe that's those that require more skills in digital technologies and software and those aspects, then they can still play a part in the transition. I don't see it's not necessarily, they're not necessarily at odds with each other, but yeah, I think that is a good question that might need to be considered.
Yeah, and perhaps looked at a little bit in further, in a bit more detail.
Mm-hmm.
Okay, so I think that's it for the questions from the audience. Just one quick question for myself. So what kind of assumptions were made on the global cost reduction estimates? What kind of assumptions about the capture or transport or storage?
So sorry, do you mean in terms of kind of efficiency or which sectors they were applied to?
Kind of the background, any assumptions that you made perhaps about, say, the storage side of things? What kind of assumptions in the background were made before estimating? Sorry.
Sure. So what we did, because it's very difficult, I think, to model, a specific length of pipeline that might be needed, or specific distribution of particular sites that would be needed at any particular point in time. What we did with with those is we combine transport and storage into a single cost component, which we reflected as a fee for those for transport and storage. But yeah, underlying that, we applied cost reductions based on estimates of the proportion globally that would be onshore versus offshore aquifers, and more broadly applied our cost distributions to those. And then in terms of the capture technologies, we applied those based on the distribution of different plant types that would be needed, and assumptions around the proportion that each type of plant makes up in the global picture. So yeah, we did try and take into account some regional aspects. So using some cost scaling, I would say certainly if we were wanting to make a much more accurate picture of what that means, you would need to look into regional factors more specifically, and probably in terms of which types of site for storage and for capture would be relevant in each location.
Yeah, that's great. Okay, I think there's no more questions there, so and that's nearly up to an hour, so thank you ever so much for your time, Catherine, in today's webinar. And so if any of the audience are interested in requesting a copy of the report, as I mentioned at the beginning of the presentation, it is report number 2020-05. So if you do want to request a report, get in touch with IEAGHG and we can send that out to you if you are a member or from one of our member countries. And thank you all for joining today.